good morning, or afternoon, whatever it is. Today, we're going to talk a little bit about what we started yesterday, and that is how do you integrate over a region that's not rectangular? And there are several ways to do this. It can be complicated, but we'll start with the easiest. And let's suppose we're actually faced with an integral, the integral from x squared to x, 0 to 1 of some function f of x and y, dy dx. First of all, what is the region we're integrating over? There is some region here, and it can be a little complicated to find it, but you find it by looking at it in reverse, I would say. X is between 0 and 1, so everything we're looking at is between 0 and 1. Then y is going to vary between x squared, that is y equals x squared. This is the beginning. And I would graph this, y equals x squared. We're only interested between 0 and 1 for x. And the end is y equals x. And we're going to be between these two. And so we're at any given x value, then we look at the region between x squared, that's here on the x squared graph, and x, that's here on the x graph. So that is a cut of the region. And then if you look at the entire region by letting the cut sweep across from 0 to 1, this is the region that we are integrating over. So I'm going to be interested in picturing these things, graphing this region, defining this region all in Mathematica, defining this region, graphing the function over this region, and then finding the volume that is under the function f of x and y, which is something like a sheet over this of some kind, and you want to find the volume between the sheet and that region. So this is one way to look at a problem. Given an integral, identify what you're looking at. So we are looking at the volume under this over this region. The other way is to be given the region. So if I'm given a region like this, how do you describe such a region? Let's call this region D for a minute. And we just saw how you can define it. For fixed x between 0 and 1, then y, the y value, will be between x squared and x. For any fixed x, this defines it, and this allows you to write the integral of a function, the double integral of a function over d. It allows you to write this as an iterated integral. The first thing you do is integrate in the y direction, or with respect to y, between x squared and x. And that's because of the way this is given. Y here is varying between two functions of x, and then x goes between 0 and 1. But you can do this another way as well. If we don't look at our cuts as horizontal, you can look at them, as vertical, you can look at them as horizontal. So that would mean fix a y value. These 2 points are 1, 1 and 0, 0, maybe not a good choice. But y, if we want to describe it for a fixed y, that is, the y value lies between 0 and 1 vertically, a fixed y value. What is x going to vary between? Well, this blue line is the line y equals x. So you will begin, for any fixed y, you will begin with the x value at this left-hand point determined by that equation, and you end at the x value determined by the other equation. The second equation is y equals x squared, or x is plus or minus the square root of y. And you want to solve this equation for x because you want this stub to begin here at some x value and end here at this x value. So this is the beginning x, and this is the x at the end. So you want to solve for those x values. This isn't exactly handy because y was given as a function of x. It's set up to do the other way, but you can do it this way also. This has two roots. One of them is over here that we're not interested in. We're only interested in the positive root. And so x will be between y and the square root of y. So this integral can be written, first of all, the integral with respect to x. And we will begin this time with the y value. And we end with square root of y, beginning and ending values for x at a fixed y. And then y will go between 0 and 1. So this is two ways of doing this same integral. Most all of these problems are some kind of theme about this. You'll want to be able to identify the regions and integrate over these regions. So practice these with Mathematica as well. And I gave you a few problems on polar coordinates, just kind of a reminder of what polar coordinates are and what happens if we change variables from rectangular coordinates x and y's to polar coordinates r's and thetas. Take a look at the little sheet that goes along with this too that has some sort of templates that you can use. I wish you well, good luck on the homework, and see you tomorrow.